kind of.
Okay. So it's a pleasure to introduce Lorenzo Laneve at Italian University of Switzerland for this quick special seminar um, about some very recent work relating some crazy math thing to some quantum thing, which is something I really like. So this is a connection between nonlinear Fourier transforms and this quantum signal processing framework for some quantum algorithms. So take it away, Lorenzo.
Thanks, Victor, and thank you for having me. As the title might hint you, today I'm going to talk about quantum signal processing and this connection to nonlinear Fourier analysis, which is um, a recent connection that was found, and that it kind of revolutionized this field. Let me start with a quick roadmap. So I'm going to introduce first what I call the QSP zoo, because quantum signal processing is really a mess in the literature, and I kind of want to do a gentle introduction to it and show you that all the possible variants that you can find in the QSP zoo are actually reducible to a single variant that I'm going to introduce. And then I'm going to talk about the nonlinear Fourier transform over SU2, along with some properties. In particular, I'm also going to relate the inverse nonlinear Fourier transform with the problem of finding the phase factors for generalized quantum signal processing. The phase factors are just a quantum signal processing protocol, as we shall see. And then the last part is devoted to actually computing the inverse NLFT with a classical algorithm that we call the Riemann-Hilbert-Weiss algorithm. Okay, please stop me if there is anything that is not clear in the middle of the talk. So let's start with quantum signal processing. What I think it's the most simple form of quantum signal processing. So assuming that you have a single qubit unitary that is parametrized by this signal Z. So in particular here we have a diagonal matrix containing Z1, where Z is some unitary complex number. T here is the complex unit circle. We call this W tilde the signal operator. Then what we do is we choose a sequence of SU2 unitaries, so single qubit operations, and we carry out the matrix multiplication obtained by intertwining this sequence of SU2 unitaries with calls to W tilde, to the signal operator. What you can see by a simple matrix multiplication is that essentially what you get is a matrix in the end whose entries are polynomials of Z, and essentially the coefficients are determined by the AK. So this sequence of what we call processing operators. So as I said, by matrix multiplication, P and Q, we are usually interested only in one column of the matrix because the other one is basically determined by the first one, since we are talking about an SU2 matrix. So by multiplication, P and Q are polynomials of degree at most n, where n is the length of the protocol. By unitarity also, we must have that the columns are normalized so that P squared plus Q squared is equal to 1 on the unit circle. And there is a theorem, which is the theorem of generalized quantum signal processing, that essentially states that any such pair of polynomials, P and Q, normalized, of degree n admits a decomposition of length n. Okay, and the proof of this theorem is a very simple induction argument that in the nonlinear Fourier analysis jargon is called layer stripping, which is an important process that can be turned into an algorithm. So if you're familiar a bit with quantum signal processing, you have you might have heard this word called phase factors, which is a bit different to what I've showed you now. What I did is to tell you, okay, we can choose a sequence of SU2 unitaries, and these unitaries can be expressed as an Euler decomposition. Okay, so in particular, I will do a ZXZ decomposition on each AK. What I do now is I replace this AK in the protocol. Then you can see that in each part of this expression, here we have that W tilde is a diagonal matrix. So it commutes with the Z rotations. So what we can do is simply take the Z rotation, for example, the alpha rotations, and move it on the other side and incorporate it in the beta rotation, for example. Then I just rename these angles here, these phase angles. And what we obtain is exactly the form that you can find in the generalized quantum signal processing paper. Essentially, you can see that the advantage of this construction is that you only have to implement the 2 rotations per step plus 3 at the beginning, and you implement any polynomial. I perceive this construction a bit more cumbersome to see, so I prefer the first one that I showed you, but it's important to keep in mind that we can always, oh, sorry, there is the light here that went off. Give me a second. Okay, so the important thing is that you remember that you can always turn the AKs into a protocol that requires less rotations. Okay, so now I'm gonna tell you a bit more about
quick thing. Sorry, so this is SU2 only. There's not like an SU3 or SUQ generalization of it, right?
There is an SU and QSP, yes, and it has certain properties, but it's not more expressive, meaning that its use is more for applications in multivariate QSP, for example. And the SU2 version has the advantage to be implementable only on a single qubit. And that's why it's the most useful. And you can also you can already implement any possible transformation on a single qubit. So gotcha. It's not so important.
Gotcha.
Okay. So, okay. Yeah, so this is the single qubit QSP zoo, actually. What I showed you earlier is just what I called analytic QSP, analytic because by the shape of the signal operator here, we have that W tilde is essentially, by the shape of the W tilde, the resulting P and Q will be analytic polynomials, okay? So only non-negative exponents of Z. As opposed to the Laurent QSP, which is came up a bit earlier in the literature, where this is the signal operator. And essentially, the only difference is that P and Q are Laurent polynomials of definite parity, just a technicality. But they are actually equivalent, meaning that you can always jump from one version to the other without, with little effort. And if you solve, let's say, one version, you can always reduce yourself to the other and vice versa. Then Laurent QSP can be turned into subcategories, let's say. The most famous is the X QSP, where the AKs are constrained to be X rotations. And let's say that the only difference is that we impose an additional condition on the P and Q. I mean, we cannot implement any possible P and Q, but we have to impose some symmetry condition on them. That's the only difference. And for theoretical relevance, I just point out that there exists also a Y QSP where we can replace the X rotations with Y rotations. There is a slightly different class of polynomials, but the idea is essentially the same. And they are both subalgebras of the Laurent generalized QSP. So, and XQSP, if you essentially by conjugating the protocol with a pair of Hadamard gates, can be turned into Chebyshev QSP, which is the most traditional version of QSP. So the first variant of QSP that arrived in the literature, where instead of having a unitary complex number Z, we have a real X, a real signal X between -1 and 1, and essentially P and Q are Chebyshev expansion of X. But anyway, everything is reducible, as you can see, to analytic QSP, which is, as I said, is the simplest one. And I'm not going to talk anymore about the others. They are important. The QSP is very important in the quantum algorithmic literature because if you conjugate QSP with some matrix decomposition theorems, like the spectral theorem or the cosine sign decomposition, as I showed you here, you can achieve eigenvalue or singular value transformations on some matrices that are encoded in some quantum circuits. And this allows you to do a lot of stuff. If you might have heard probably of the quantum singular value transformation in particular, because it allows you to unify and simplify a lot of known and new quantum algorithms. So that's why QSP is so important. And I'm gonna now show you how we use QSP in the context of eigenvalue and singular value decomposition. So essentially, we want to implement some transformation, f of z, so some function that will be applied to our eigenvalues or singular values. So what should we do here? So the first one, the first point is design. So we find a polynomial, p of z, that approximates f of z to desired precision. And in general, what we do is having higher and higher precision requires polynomials of higher and higher degrees, which translate into QSP protocols of higher and higher length. Okay, so in other words, deeper circuits. The second part is completion. So once we find our desired polynomial P, we find a complementary polynomial Q such that P and Q can be embedded in a quantum state, because remember that we ultimately need to embed these polynomials in a unitary matrix. So it's important to find such a polynomial. And once we have our pair P and Q, we have extraction, which is essentially the last step, which is extracting an actual QSP protocol that implements the pair P and Q that we found. Okay, so the first part is actually easy. It's basically using classical approximation theorem like Fourier or Chebyshev expansion, depending on your variant of QSP or which interval you would like your approximation to be good. But usually they are standard techniques and they are not a super concern. On the other hand, the other two points are actually a challenging numerical problems that have had an intense line of research in the past years. So let me talk about completion first. So as I said, given a P, find a complementary polynomial Q. Let's do the usual mathematical questions that we can ask. Does such Q always exist? The answer is yes, and this arrives from a result in polynomial factorization theory known by the Fourier theorem. Is it unique? That's the second question. And unfortunately, the question here is no, not at all. Because if you think about it, if I take some complementary Q and I multiply this polynomial by a global phase or a monomial, then the modulus is preserved. And so this new Q will still be a complementary polynomial to our P. On the second part, there is also a not so trivial part, which is if I take any Q, any root of Q, and they always exist by the fundamental theorem of algebra, and I transform it, basically I do 1 over R star. So I take the reciprocal of the conjugate of this root and I replace to the original root of Q. This transformation also preserves the modulus. So you can see that even if we fix the global phase, we can have up to 2 to the n possible complementary polynomial for a given polynomial P of degree n. So there is a huge problem here with the uniqueness of complementary polynomials. And now suppose that we choose some complementary Q, okay? We want to compute also the processing operators implementing P and Q. We know that they exist by the main QSP theorem, but the question is also here, is such a sequence of processing operators unique? And the answer also here is unfortunately no. And you can see that the thing is, as we saw earlier, Z rotations commute with the signal operator. So for example, if I take this beta rotation here, I can always switch the position between the signal operator and the beta Z. And what happens is that I'm changing the 2 surrounding processing operators, but the final result doesn't change, okay? So P and Q are actually implementable by different sequence of processing operators. So you can see that uniqueness is a huge problem in QSP. And this has been a problem because it didn't let us define a solid and well-defined theory of single qubit quantum signal processing. And this is where the nonlinear Fourier transform arrived to solve this problem in some sense. So let me briefly show what the nonlinear Fourier transform over SU2 is. So imagine that you have a complex sequence, just like the linear Fourier transform you're probably familiar with. A sequence that might be also infinite in general. We define informally the nonlinear Fourier transform as this formally infinite product, where you can see these are matrices that are parametrized by Z. Okay, so yeah, you can see that this term is exactly like the linear Fourier transform, except that instead of summing all these terms, we are multiplying them in as SU2 matrices. So the result of this infinite product will be a function from the unit circle to SU2, and in particular, this matrix is given essentially is determined by the top row, right? Because an SU2 element is always determined by the top row. So I just take this pair of functions, A and B, And from now on, I'm gonna define the NLFT as these two functions, this pair of functions, okay? But always remember that they are simply an SU2 element in disguise.
Sorry,
Yeah?
so f is a function of z, and z is e to the I phi.
F is a sequence.
Okay, sorry,
Okay.
f tilde, or whatever f, what do you call that thing? The NLFT of f is a function. It must be a function of an angle if you want it to be like Fourier-like, right?
Yeah, like z is a complex number of unit modulus. So we
Okay,
are still working on the unit circle.
good,
So yes, okay.
good. And then, right. And then what's this bottom thing? You have a infinite product of matrices. So how does it help you to express one matrix as a vector if you have to take an infinite product of them?
Well, basically, you can see that the entries of these matrices will be essentially infinite Fourier expansions, right? And I call these infinite Fourier expansions A and B, like the functions
this
that appear.
F is literally equal to this other matrix that's got A of Z, B of Z, and blah, blah, blah. And it's unitary because,
Because it's a product of unitary matrices, exactly.
good,
Yes.
good. And then, so it's equal to that. And then on top of that, you distill the vector out of it. Got it. Thanks.
Okay, no problem. Okay, so generally, the NLFT is well defined also for one-sided infinite sequences. But since QSP has finite length protocols, I will as well assume that F will have a finite support. Okay, so it will have a certain support, and if this is the case, then A and B are not actually general functions, but would be Laurent polynomials. Okay, so polynomials that might have both positive or negative exponents in Z. And here is where we are getting closer to QSP. So let me give you some intuitions about the properties of the NLFT. So imagine that you have a sequence F that goes from -2 to 3. What happens is that by constructions, as we said, since it's has finite support, then A and B will be Laurent polynomials, but ranging which frequencies? So B, by construction, will always follow the support of F, meaning that since F starts from -2 and then to 3, B will have the first term that begins with Z to the -2, and the last term that has Z to the 3. Okay. Whereas, and this is the interesting part that will overcome some non-uniqueness problems, A, on the other hand, will always be bounded, meaning that the support of A will always end up at the zero frequency. Okay, so A will always have only negative frequencies, and A0, so the constant term, will be always the last one in the polynomial. And also, A0 will always be real and positive. This, again, sorry. Okay, sometimes that's to happen. Okay, so the point here is that if I change the support of F, you can see that B will always follow the support of F, while A will have the same size of the support, because by the fact that A and B must be the A squared plus B squared must be equal to 1, because they are the row of an SU2 element. This also implies that the support of A and B must be equal in size, but A is always fixed to end up at the zero frequency, okay? So this is what happens, essentially. In some sense, this tells you that the real protagonist of the NLFT is B. You can think, if you want to find analogies with the linear Fourier transform, you have to look at B. A is, in some sense, only a complementary polynomial that doesn't have the same degrees of freedom of B, and it's only a way to make B appear in an SU2 element, essentially. So let me give you some other properties that you might find familiar. Essentially, the first one is that if you shift the support of F, in particular, if you shift F to the right, for example, by 1, then B will be multiplied by Z. This is also what happens with the linear Fourier transform. But remember that A doesn't change because the support of A is always fixed. The second property is the composition or concatenation property. Essentially, imagine that if the support of F is entirely on the left of the support of G, and this means that they never overlap. So F plus G doesn't really sum anything. It's just a concatenation of the two sequences, essentially. Then the NLFT of the sum of the concatenation of the two sequences is just the product of the NLFT of the single sequences. This you can see it from the product. And then we have the phase property, where essentially what you have here is that if you multiply f of n by some phase, then this phase is reflected directly to B again. This still, you can see from the shift and phase property what I mean that when I say that B is the actual protagonist of the NLFT. You can imagine that this property, unlike the linear Fourier transform, doesn't hold for all the complex numbers, because this would break the fact that A and B are in an SU2 element. Okay, so this is something different from the linear one. But these properties are important because they allow us to look at the algorithm for the inverse NLFT, as I'm going to show you in a second. But first, I want to show you how the NLFT corresponds to generalized quantum signal processing, as I showed you, as the protocol I showed you before. And I hope that this visual proof is insightful to you. For me, it was. So what I'm going to do now with this expression, you can see that now the product is finite because the f is finitely supported. So we assume to have f that goes from f of 0 to f of n, okay? And in particular, this means that A and B will have degree n. So what I'm going to do here is I'm going to take this matrix and I just decompose it in this way. So I'm just removing the Z from the middle matrix. And you can do a quick computation of these matrix products to see that this matrix is equal to the previous one. Then what I can see here is that these two matrices are actually the signal operator in QSP that I showed you at the beginning of the talk, raised to some power. So I can replace these two matrices with W tilde to the K and W tilde to the negative K. Then I'm gonna take this matrix here, and I'm gonna designate this matrix to be my processing operator. So I call this matrix AK, which will be the AK that will appear in my QSP protocol. And then now I just unroll this product. So I just take the product, I just write down the elements of this product in this sequence. And now you can simply notice that in the middle, the various occurrences of W tilde actually appear that they belong to contiguous elements of the product. These, they simply sum up to 1, right? 0, 1, minus 1 plus 2, minus 2 plus 3, and so on. So I can just simplify them and write down W tilde here. And here you can see that this in the middle is our QSP protocol. And these matrices on the borders, well, I mean, W tilde 0, you can imagine it doesn't do anything, while W tilde to the n just shifts A, because remember that in the NLFT, as I told you, the support of A is always on the negative side where the last frequency is the 0 frequency, whereas this W tilde to the n will just shift AN so that in the QSP protocol, AN will appear to be an analytic polynomial, as we should expect from QSP. So let me wrap up this result. Essentially, this says that assuming that you have this pair A and B, whose inverse nonlinear Fourier transform is this sequence f0 up to fn, then I can always choose, I can always construct a sequence of processing operators in this very simple way from the FK, and then construct a QSP protocol with those. And what I get from the QSP protocol is exactly my B. And okay, yes, also A, but A will always be chosen to be to just be the complementary polynomial to B. So our desired transformation will be B, okay? And so the FK will completely determine the QSP protocol in any variant, also generalized QSP. Now a bit of intuition also on the subcategories compared to the sequence. So first of all, we have that if Fk is a purely imaginary sequence, it's happening, or whatever. If the Fk is a purely imaginary sequence, and this is the case originally found by Alexis Italia in last year, essentially, then what we get is what I called in the QSP zoo XQSP, because all the AK will naturally be X rotations, and the phase factors can be simply retrieved from the FK by simply computing an arctangent. On the other hand, if you see that if you happen to have a real sequence, what you get is essentially YQSP, because the FK here and the construction I showed you earlier, you can see that as the SU2 elements that appear are essentially Y rotations. And this means that analogously to XQSP, also here, the phase factors can be retrieved by an arctangent. And then we have the most general case where FK is a generally complex sequence. Here, P and Q can be any complex polynomials, and we are indeed in the case of generalized QSP. And so we have this slightly more complicated way to retrieve the phase factor from Fk, but it's still perfectly viable. An important thing here is that if the nonlinear Fourier transform is bijective, and this is the case, meaning that from the fact that the nonlinear Fourier transform is bijective, we get a definition of what I called in the paper canonical phase factors. So a set of phase factors, a set of GQSP phase factors that satisfies a particular condition. And we can actually prove that this set of canonical phase factors is unique for a given polynomial P. And this, in some sense, is nice because it essentially states that nonlinear Fourier analysis solved our uniqueness problem in QSP. And another point which is very elegant, in my opinion, is that if P happens to be in a subcategory of QSP, for example, X or Y QSP, then the canonical phase factors automatically fall in the corresponding subalgebra. So by simply using the inverse NLFT, you will get a protocol that has only X or Y rotations. So, and this saves you that extra rotation per step, okay? This is nice. This is nice because it simplifies the algorithms to find phase factors based on the NLFT. Okay, so the last part is about actually computing the phase factors on a classical computer. Because as we said, computing a QSP protocol is important in applications like the quantum singular value transformation and so on. So here again, what we have is some desired polynomial B of Z. The first step is to find some complementary polynomial such that this pair AB is in the image of the NLFT. And the second step is to find the actual inverse nonlinear Fourier transform of this pair that we found in the first step. And then you know that once we have the inverse NLFT, as I showed you in the previous parts, we can retrieve the QSP protocol easily.
So once you find A, then you reduce the problem to finding a QSP decomposition.
Yeah, actually, inverting the NLFT is mathematically equivalent to finding a QSP decomposition. That's the point.
But you have that extra A you got to find. But you're saying that's just the standard step.
What do you mean it's the standard?
Like
Sorry.
Do you need the A in the QSP decomposition as well, I guess. Okay, I guess.
Yes, yeah.
Okay.
It's an integral part of the algorithm,
Okay.
the completion part. Okay, and this is actually the first that I'm gonna talk about. So the first one, it's Weiss algorithm that tackles the completion problem. So the idea is actually very simple. So you have to find some A that completes B. What you can do as a very first attempt is to take f of z, which is equal to the square root of 1 minus b squared, right? And this, you can see, it trivially completes B, meaning that trivially satisfies this equation. The problem is that f is never a polynomial, actually, because it's always real on the complex unit circle. So and polynomials usually polynomials never satisfy this condition. So now I'm gonna invoke a bunch of complex analysis stuff. So the idea is simple because we take the logarithm of this function, this logarithm of f here, and you can see that if f is real, then also the logarithm of f is real, right? So now if I add an imaginary part to this function and I exponentiate it back, then you know that the modulus of the function only depends on the real part of the exponent, right? Because the imaginary part only contributes a phase in the exponential. So the question now is, can we find an imaginary part v of z such that the full function here, by adding this imaginary part, the full function becomes an analytic function? And this will be enough because if you then exponentiate back, the exponential of an analytic function is an analytic function. And in particular, you can prove that since analytic function has a very rigid structure, this function will also be a polynomial because we know that polynomial exists by the Fourier's theorem. So now the only question is how to compute this V, and this can be done by solving the so-called Schwarz problem, which resorts to computing this very simple integral on the complex circle, which is called the Schwarz integral formula. If you're a bit familiar with complex analysis, the Schwarz integral formula is the complexification of what is known as the Poisson kernel. And so what we obtain here is just that. So we take the logarithm of this function that we can compute from B. We add this imaginary part, and then we exponentiate it back to obtain our polynomial. And the hard part in analyzing Weiss algorithm is actually showing that this can be done with a pair of fast Fourier transforms. Okay, so if you take sufficiently fast Fourier transforms with a sufficiently large modulus, you can apply the Schwarz integral formula to the Fourier expansion of f with little numerical error, essentially, and this is how you get away with it. This is the actual technical part of the algorithm, but the idea is the idea behind is quite simple, actually. Then the second part, which is about extraction, regards the so-called Riemann-Hilbert factorization. It's the Riemann-Hilbert algorithm. So also here, the idea is very simple. What we do is notice that the first element of the sequence is actually very easy to read from AB. It can be computed with this very simple formula, and this B0 and A star 0 are simply the coefficients, the first coefficients of A and B. So now it would be nice if we could compute the same, like the other elements of the sequence in the same way, right? And this is actually what we do. So essentially, we are factorizing AB. This is the so-called Riemann-Hilbert factorization in this way. So AB, remember that these are SU2 elements. So the SU2 matrix composed by AB will be factorized into a product where the first element is basically the NLFT of this point alone, so the NLFT of F0, and the second SU2 element will be the NLFT of the rest of the sequence, okay? And this is essentially invoking the concatenation property of the NLFT that I showed you in the second part of the talk. So now what we can do, since we have these two polynomials, is to compute F1 in the same way we computed F0. So we just apply this formula to this pair of polynomials. Okay, and then we do the same thing which involves solving a linear system. We can find the Riemann-Hilbert factorization by solving a linear system on a certain matrix given by Weiss algorithm. And by to compute the other terms, we do exactly the same thing. We do a cut, for example, for F2, we do a cut here. For F3, we do a cut here, and so on and so forth. And we read the coefficients one by one. The complexity of this algorithm is n to the fourth, essentially, because solving a linear system takes n cubed, and we have to do it n times. So the complexity comes from this. Okay, so Alexis Italia last year proved that this algorithm is actually numerically stable, but the point is that you could see that it's not very efficient, like n to the fourth is very bad. But what we can do essentially here is apply these two improvements that were found in two subsequent works essentially in the last year. The first one is the so-called half Cholesky method, where essentially what we can observe is that the linear system needed to find each fk are quite similar, and they can be solved all at once by decomposing a certain matrix. And in particular, we have to do a Cholesky decomposition of this matrix here. And this theoretically would take n cubed, not n squared. But Ni and Ying proved that this matrix actually exhibits a certain structure. So it's a very well-behaved matrix. So we can extract the information from the Cholesky decomposition that we need without actually computing the full Cholesky decomposition. And so this turns into an n squared complexity. And then the best algorithm that we know is by Nisar, Carl, Lin, and Ying by this year, where essentially, very roughly speaking, the idea is to do a divide and conquer approach where we split A and B in two equal parts, and then we recursively compute the inverse NLFT in these two subproblems, okay? And by the master theorem, you can prove an n log squared n complexity, so a near linear complexity with this algorithm. Very quickly, I want to show you also some numerical experiments. You can find the implementation on my GitHub, and perhaps if you ever need to compute QSP protocols, I hope that this package would be useful to you in some way. So you can see this is the time that, well, the very worst one is the Riemann-Hilbert-Weiss algorithm, because, yeah, you know, n to the fourth is very bad. There are also other two methods, namely the Prony's method plus layer stripping and the convolution optimization plus layer stripping. There are not too many results for generalized QSP. The literature of phase factors for the traditional for XQSP are much more consistent. There were many more results than generalized QSP. So the NLFT is also a very huge improvement for GQSP in this sense. But you can see that the very best algorithm still is the nonlinear fast Fourier transform running in near linear time, which can find a QSP protocol even of a million-degree polynomial in essentially 300 seconds. So very fast. Well, sorry, you can see also that the times between the Alf-Cholesky method and the two previous methods are quite comparable. But what really changes here is the numerical stability, because you can see that even with very low degrees, this is the completion forward error. So the forward error of the complementary polynomial before extracting the QSP protocol, you can see that the convolution optimization is very poor, and the Prony's method fails after a very small degrees, actually, while Weiss algorithm is it remains certainly undefeated in this case. While for the forward error for the inverse NLFT, well, since the complementary polynomial was of a very bad quality in the first place, we cannot expect layer stripping to do miracles, of course. And so you can see that after some point, we get complete garbage on the previous method, whereas the methods based on the nonlinear Fourier transform are very consistent and very stable. And if you want exponentially better results in the forward error, you just have to double your precision because it's numerically stable here. Okay, so let me conclude here. So as I showed you here, the nonlinear Fourier analysis turned out to be a very precious tool to analyze QSP, not only because it actually gave a very practical and numerical method to find a QSP protocol, but because it gives a very consistent and a very consistent mathematical foundation for QSP. And in this paper, I try to enforce the fact that to stress the fact that they are actually equivalent as theories. And so whenever you want to compute the phase factors for QSP or the inverse NLFT, they are exactly the same mathematical problem, essentially. And this also means that since the NLFT is well understood for one-sided infinite sequences, where in this case B is not a polynomial, but it's a general analytic function on the unit disk, this gives us for free a theory of the so-called infinite quantum signal processing. Why is this quantum signal infinite QSP important? Well, you can think of it as a way to simplify the analysis of QSP protocols, because essentially, instead of designing a polynomial that approximates our desired functions, I can, in theory, compute the inverse NLFT of my desired function without truncating it to a polynomial. And then what I do is just to truncate the inverse NLFT. We don't have an algorithm for that, but mathematically it can still work like that. And perhaps in the future, we might have some algorithms that are stable also in this sense. So in some sense, it would save us the design part of the polynomial. And then the last part, the last point here, which is like the one that I'm actively trying to work on, is that NLFT might be promising in the mission of finding a characterization of multivariate QSP. This because while we know what happens with quantum signal processing over a single variable, we don't really know what happens with different variables. And this is a work in progress, but we managed to define appropriately an NLFT over several variables. And what we prove is that they are equivalent to multivariate QSP as is already proposed in the literature. Okay. I can anticipate you that the biggest problem that we are facing here is completion, because while a complementary polynomial always exists in the univariate case, this might not be the case when we have multiple variables. So characterizing such polynomials is a very hard task. This is the end. So thank you for your attention, and I'm open to questions.
Thanks. That was great. Yeah, I'm trying to make the clap signal.